Hello, hi, I'm Yu from Taiwan Tech.
I'm Chen Hongyu from Sida.
Ling from National Taiwan Normal University.
Okay, so you introduce yourself.
Hello everyone. We're the music team from National High School. I'm Jason Lee, the team leader of our team, and this is Ryan Lee, this is Amy Huang, and this is Pearl Yu. Thank you.
And hello everyone, we are team ECN 1917, and we are from National Drama Girls Senior High. I'm Zhen Zixi. 胡玉玲、陈如颖、赖慧敏、张宇。Thank you.
Okay, so okay.
Hello everyone, I'm the captain of PF4 and my name is Chen Yujing, and this is Lin Haozhan, Lin Yuchen, Wu Weizhong, Chen Bowei, and we are from Foshan Senior High School.
Okay. And so the opponent challenged the reporter for the problem. So opponent.
Okay, so we're gonna challenge problem number 2.
We will set the challenge.
Okay. And for the preparation for the reporter.
可是我不知道不可爱这样会不同你讲的也是没错，我觉得对我们来讲是很多的地方。我们上面的一个本来是，本身也是有一定的。
这边都有，对不对？啊，这里不用写了。
不用，
这是比较参考的。
对对对。
Honorable juries and fellow competitors, I'm the reporter from the PF4 High School. Today I'm going to talk about the problem 2, oscillating sphere. Here is the problem statement. A light sphere with a conducting surface is suspended from a thin wire when the sphere is rotated about its vertical axis, thereby twisting the wire and then released. It starts to oscillate. Investigate how the presence of the magnetic field affects the motion. And here's our main focus, how different parameters affect the sphere oscillate. And here is our outline. The first is observation, about including the video, damping, and amplitude decay. And the second is about our theory. It's about eddy current, charge density, and net torque and decay time. And the third is experimentation, about the equipment, setup, and the parameters investigation. And the last is including. First, about our observation. In this video, you can see we give the sphere an initial rotation angle. So by the torsion, the ball starts to rotating. And we use these two coils to provide the sphere a uniform magnetic field. So we want to research what the effect of the magnetic field to the sphere. And let's talk about the amplitude decay. In this diagram, you can see this is a diagram about the theta, the amplitude of the sphere rotation to time. And the black line is without the magnetic field. And we can see the black line decayed over time. And for the red line, it is the condition when we provide magnetic field to the sphere. And you can see that the theta of the red line is a little bit smaller than the black line. And the red line decays over time too. And what causes the decay of the black line? That is because the air resistance and the torsion damping. And what causes the theta of the red line is a little bit smaller than the black line? That is because of the magnetic damping. And second, about our theory. Our theory is first about the eddy current. We can imagine the ball consists of so many coils, and the magnetic field gets through this coil. And we give the sphere an initial rotation angle, so the ball starts rotating. And when the ball starts rotating, it causes the variation of magnetic flux. And by length flow, it generates induction current. And you can see here, when the magnetic field is forward and the current is upward, so it makes a force to this direction. That causes the magnetic damping. And our theory about the charge density, we assume the sphere thickness is much smaller than the sphere radius and only one layer electronic on the surface. And this is our equation about the current density. And we search the continuity equation. And because there is only one layer electronic on the surface, so the charge distribution is constant. And we calculate the magnetic force, and we get this equation. And we also get the charge density equation about the low T equation. And the low T means the tangential charge density. And we establish a coordinate system of the sphere. And let's calculate the net force. You can see this equation. After integral, we can calculate the net force equals to 0. And we calculate the net torque by current density and the moment of inertia, and get these two equations. And the omega means the angular frequency, and sigma means the conductivity of the sphere. And we combine these two equations to get to get this, and that indicates that the spinning sphere decelerates exponentially, like this. And then we define magnetic decay time as alpha. And we consider air resistance and the wire torsion, and we can get the tau equal to minus kappa theta. And the kappa means the torsion constant, and the alpha, just like I just mentioned, is magnetic damping, and the gamma is frictional damping, and the theta means the total decay time. Alpha and gamma represent the magnetic damping and frictional damping. And we can get this equation because the amplitude decays exponentially. And about our experimentation, we use the Gauss meter to measure our magnetic field strength. And we use the magnet wire about 0.5 millimeter to bound on these two coils. And we use the camera to shot the videos. And the sphere is suspended with the magnetic wire about 0.1 millimeter. And the sphere we use is stainless, conducting and hollow. And you can see the coil beside the sphere is called Helmholtz coil. The function of Helmholtz coil is to provide a uniform magnetic field to the sphere. And we can use the power supply just to adjust the magnetic field in this area. And about our setup, the first step, we power up the Helmholtz coil, and the second, we adjust the sphere to the initial rotation angle. And the third, we record a video until 600 seconds. And the fourth, we use tracker to analyze the amplitude. And we can see when we provide 12 Gauss and 25 degree initial rotation angle to the sphere, and we can get an amplitude decay diagram about theta to a time like this. And we find the peaks of the theta and do the exponential analysis, and we can get the theta here. And we find magnetic decay time, alpha, used as the theoretical value. And we measure the total decay time in non-magnetic field situation. And we measure the total decay time in non-magnetic field situation. And in this situation, there is no magnetic field, so the alpha is not exist. And then we can calculate the theta. It's about 340. And we use this data, get into this equation to get the frictional decay time. Gamma is about 170. And we use these two data to get a new equation about the non-magnetic field situation. And our first experiment is about a magnetic field. And we provide 12 Gauss, 10 Gauss, 8 Gauss, 6 Gauss, 4 Gauss, and 2 Gauss, and calculate the theta. And we can get the diagram about the magnetic decay time to a magnetic field. And the alpha TH means the theoretical value of the magnetic decay time. And the alpha EX means the experimental magnetic decay time. And about the discussion, we can find when the magnetic field is increased and the experimental error is decreased. Why? Because when magnetic field is big enough, magnetic damping will be the main damping term in the rotation system. And when on the contrary, when the magnetic field is small, other frictional damping, like the air resistance and the friction between the wire and the sphere, become bigger in the system. And you can see in the condition of 12 Gauss, the experimental value and theoretical value is much closer than the 2 Gauss. And our second experiment is about the initial rotation angle. And we provide 120 degree, 90 degree, 60 degrees, 30 degrees. And about the discussion, and you can see a diagram about theta to the time here. When the initial rotation angle increased, the frictional damping term about the torsion of the wire increased, and the variation of the amplitude decay increased too. You can see the variation of the amplitude is by, we use the red line as an example. You can see the variation is here to here. And getting to the conclusion. About our problem statement, we investigate how the presence of the magnetic field affects the motion. And we find the parameter is about the magnetic and frictional damping. And when the rotation axis is vertical with the magnetic field direction, and it generates a resistance opposite to the sphere rotation direction, and the amplitude decay is exponentially. And the magnetic field square is inversely proportional to the magnetic decay time. And when the initial rotation angle increased, the frictional damping term increased, and the variation of the amplitude decay time increased too. Thanks for listening.
Okay, so the first question. Can you please turn to page 6?
About this diagram.
So, can you briefly explain why it's decaying?
About why it's decaying, because I just said when the black line, that decay reason is about the air resistance and the wire torsion damping.
Okay, actually, I want to ask, how do you calculate the delta? Because how do you calculate it?
How do I calculate the theta? We use the camera to shot the video, and we use the tracker to get our data.
Okay. So, since you consider it as an origin, right?
Yes.
So, did you calculate it will have a periodic motion, right?
About the periodic motion, yes.
Okay, so did you calculate it?
No, we didn't do the search about the periodic motion, but we do the research about the initial rotation angle and the magnetic field strength.
Okay, so do you think you can calculate it and to get more like a result?
Maybe we can do the data and we record the period of the rotation.
Okay, so can you characterize the magnetic field?
Characterize.
Yes.
The magnetic field we give to the sphere is uniform, and because of the uniform magnetic field, it won't have other.
Okay, we'll talk about it later.
Typt the opponent then.
Okay. So, I'm the opponent from Team CYJ. My name is Brian Hu, and today I'm gonna oppose problem number 2, oscillating sphere. So the problem statement are: a light sphere with a conducting surface is suspended from a thin wire. When the sphere is rotated about its vertical axis, thereby twisting the wire, and then released, it starts to oscillate. Investigate how the presence of a magnetic field affects the motion. So the main focus is that the presentation they have is how different parameters affect the sphere oscillation. Here is a summary from about the point. So the phenomenon they have are damping, rotating, and oscillating. And the theory they use is to explain the motion are eddy current, charge density, net torque, and decay type. Okay, so the experiments, we can see that the parameter, there are 2 parameters. So the first are magnetic field, and the second are initial rotation of angle. So the advantages I want to give to the reporter are they have a well presentation and a detailed explanation in theory. And the suggestions I want to give to the reporter are lack of parameters, and we want to discuss it later. Okay, so the discussion I want to make about the observation, we can have the discussion about motion, rotation, and the theory part we can talk about magnetic force or decay. And about the experiment part, we can have the setup and parameters. And to the conclusion part, we can discuss about rotational angle or magnetic field. So yeah, thanks for your attention, and I would like to switch to the discussion. Okay, so the first question I want to ask is that you haven't finished it yet, right?
Yes.
So what I asked, can you characterize the magnetic field? Because in your experiment, I think you already characterize your magnetic field as an important thing to do.
Yes. And the magnetic field, if the sphere is uniform to the x-axis, then I just mentioned we create the coordinate system of the sphere.
Okay, so you mean that x-axis, right? Do you try to put the magnetic field like vertical?
Put the magnetic field to vertical?
Yeah.
Because there is a thin wire suspended from here. And if you use the coil to the up and the down, that makes effect. So we put the coil beside the sphere.
I think like you can think about the setup later, but I think it's crucial to discuss about whether the magnetic field are parallel or vertical can affect the experiment. So how do you think it will affect the experiment if it's like vertical, like the magnetic field are from vertical?
If the magnetic field is vertical, and what I just mentioned, we consider the sphere consists of so many coils, and when this is vertical, that may cause the same effect, but the gravitational effect may be more.
Okay, so you think that gravitational would affect more than the magnetic field, right?
No, and
If it's put in the vertical.
if we put it to the vertical, we have to use a thin wire from these 2 sides to hold the sphere. And because of these 2 thin wires, the torsion may be more effective.
Okay, so torsion, so do you think that gravity can affect?
Gravity affects.
Yeah.
Yes.
Okay, so another question I want to ask about the setup is that how do you generate your magnetic field?
How do I generate?
Generate the magnetic field.
We use the Gauss method to measure our magnetic field.
So generate. So how do you like manufacture the magnetic field?
This is a coil. and the power supply that supply the electricity to the coil, and the coil provide the magnetic field to the sphere.
Okay. Can you please turn to page 8? So you mentioned the eddy current, right? So
Yes.
what direction do you think is the eddy current influencing the motion?
And we can see a diagram here. When the magnetic field is forward, and that the current is upward. So the force is to this direction,
Yeah.
and this is the rotation direction of the sphere, and this causes the magnetic damping.
Okay, so cause of magnetic damping is can you explain why does it cause the magnetic damping? More clearly.
More clearly,
Yeah.
just I mentioned, this causes the force to here,
Yeah.
and the direction of the force is opposite to the rotation direction
Yeah.
of the sphere.
Yeah.
So that causes the magnetic damping.
Okay, so please turn to page 13.
About this diagram,
Yes. No, 13, 13. 13, sorry. Okay, so you mentioned the kappa, right?
Yes.
So can you briefly explain how the kappa can like compare to the experiment result?
the kappa means the torsion constant, and when we change the material of the wire, that change the kappa.
Okay, so how does it affect the result?
And how does it affect the result?
Yeah.
When the torsion constant affects the cap,
Yeah.
the torque of the sphere rotation.
Okay. So, do you think are there any parameters that you can compare it to this kappa?
To the kappa,
Yeah, the parameter that you did.
no, we didn't do the research about change the material of the wire.
Okay, so maybe you can add more parameters. So that's why I can suggest you that you can add more parameters.
Okay.
So that's one of them. Okay. So yeah. So please turn to page 16. Okay, so record a video. It's a small question, but I want to ask why is it 600 seconds? Is there any is this strictly constrained or just how you record?
The maximum length of the tracker video is 10 minutes.
Yeah.
So we record the video until 600 seconds.
But is this necessary?
Is it necessary?
Yeah.
And we use the maximum length so we can get a full rotation about the sphere.
Okay, so so if the motion is under 600 seconds, like will it still be recorded until the 600 seconds?
Yes.
Okay. Okay. Yeah, this is a part of the question. Okay. So please turn to page 30. Yeah, this is example 30. Can you briefly explain how the graph works? Like the motion here. Why does it occur?
Why does this occur? Yeah. And this is data after we do so many experiments, and we get an initial rotation angle increase. Then you can see the variation, just like this, about the black mark. And this is the variation of its work, about its amplitude, and the decay time increase also.
Oh no, I mean how did it occur? How does the motion transfer into this graph? The motion, which motion does it which motion does it represent?
How does motion does it represent? plus peak. We get a peak.
Okay, so that graph is a peak.
Yes.
All of a peak. Okay, so I want to go back to the theory property.
It's about eddy current.
Okay, I'll just. Why does the magnetic field cause it then?
Just I mentioned that
Okay.
because this force.
Okay. So do you think that inducing currents have any source of relationship? Inducing current
Inducing current.
have any source of relation in this kind of decay?
The current is this, or what is current you mean?
Inducing current, like when a like I'll briefly explain it. Like when a magnets are moving in a like a coil thing, it would generate a inducing current.
Yes, and the inducing current is this. When the magnetic is
Also, how does the inducing current affect the decay? Affect the decay.
when the variation of the magnetic flux that causes the appearance of this current, and we can use the right-hand rule that we can get the force is to this direction.
Okay.
That causes the magnetic damping.
Okay. To this, can you show the formula?
Formula?
Yeah. So, can you compare it to any experiment you have done? This theory.
In this theory,
Okay.
and the alpha means the magnetic damping, and we use alpha as the theoretical value, and we change the magnetic field, so we get a different theta as the data, and the gamma means the frictional damping.
Yeah.
We change the initial rotation angle, so the frictional damping is also in the parameter.
Okay. So, did it fit in your experiment?
Yes.
Okay. So, how exactly? Can you clearly explain? Like fits in the experiment.
Fixed the
Fits.
here.
Oh, okay. I mean, which part of the theory, which part of the formula is? Can you like explain which part of the formula you use is directly compared to this?
Compared to this.
Okay. Yeah.
And we can use this diagram to evidence our equation.
Okay. So what do you think that causes this these two things that they have different value? So
Yes.
the experiment yes. So the experiment error. Do you think that are there any more like other value that can affect the result?
Value affect the result.
Oh no. So are there any more factors that can affect the result?
And this experiment is about the magnetic field.
Yeah.
And if the magnetic field
Okay, so the opponent summarized the discussion.
Okay, so the first I asked him about why does the magnetic field cause the damping? So he uses the Lorentz law and their theory to explain it that the forces will cause the damping. And I also asked him about whether the vertical or parallel magnetic field can affect the experiment. And they replied that they didn't do the experiment, but they think it will affect the experiment. So so I suggest that the reporter can run more parameters. Like also in the torsion pendulum, they didn't calculate the periodic motion, and I think they can calculate it and to get more results. So thanks.
The question of the reviewer.
So, the first element has both reporter and the opponent. Do you think it's a kind of under-damping motion?
Under-damping motion.
Do you think it's a kind of under-damping motion?
Can you explain?
Okay, so skip this question. Let's go to the next. Is it a kind of regular rotational motion?
Regular rotational.
The motion of the ball.
The amplitude of the rotation is decay.
Okay, thank you. And
So regular rotation, I think it would also magnetic field can affect it from being a regular.
okay, thank you. And at least how many voltage it needs to affect the motion of the speed?
How many?
Voltage, magnetic fields.
Yes.
At least how many?
How many magnetic field?
Like you provide like how many fields?
Yes, just the data here. I provide 2 gauss, 4 gauss, 6 gauss, 8 gauss to the 12 gauss.
Okay. Since the greater the magnetic field is, and there'll be like more magnetic resistance. So do you think that there'll be a limitation?
A limitation?
Yeah. Since with greater magnetic field, the magnetic resistance will be like bigger.
We didn't do the research about the boundary condition of the magnetic field.
Okay. So do you think?
Yeah, I think there would be a boundary condition, and I think the reporter can do it.
Okay. And do you think that instead of magnetic damping, air resistance, and torsion damping, are there any other torque?
Are there any other torque?
Yeah. In this.
In this experiment,
Yeah.
I think you mean whole torque.
Yeah.
Like,
Okay.
I'm not sure about this question.
And do you think that it's important to have a uniform magnetic field in this?
Yeah, it's
Okay, thank you. And also, do you think that what is the material of your sphere?
The material of our sphere is stainless.
Okay. And do you think that the size of balls will it have a limitation? Like too big or too small? The experiment it can't.
The size of the ball also affect the mass of the ball, and we give the initial rotation angle, and maybe we can give a bigger magnetic field, and that may also cause this phenomenon.
And have you measured the torsion constant, which is the kappa?
No, we didn't do the research about it.
And,
Okay.
okay,
So prepare for the review. So the review takes the floor.
Okay. Hello everyone, I'm Rudy from Team ECN 1917, and today I'm gonna review to you problem number 2, oscillating sphere. And here is the problem statement. We think that it will mainly focus on investigate how does the magnetic field affect the motion of the pole, and how does the damping motion affect the theta t diagram of the pole. And here is overview of the reporter. First, phenomena they use damping, and when amplitude decay, they use magnetic damping, air resistant torque damping, and provide or without magnetic field. And for theory, they got damping time. They use combine the net torque equation and the amplitude decay, and the net 2 by current density, the net force, and eddy current. And for experiment parameters, they change the value of magnetic field and initial rotation angle. For conclusion, when initial rotation angle increase, the friction damping time increase, decay of the magnetic decay time increase. And for the overview of the reporter, first, investigation sticks to the proper statement, the conducting force surface of a sphere, and nice demonstration on the experiment device and while theory illustration. But for cons, didn't clearly explain the phenomenon. They only show how the data fit the calculation, and not fully show the torque of the magnets. And also they didn't show that when they test the magnetic field, the distance between the device and their experimental things. And for the overview of the opponent, summary how they generate a magnetic field. And the coil provided magnetic field, and they discuss about the direction of eddy current. For cross, point out the error point between the magnetic field and theoretical line and experiment. For cons, they have no they didn't give that much self-opinion, and too much focus on something that is not reported important since the reporter had just talked about it in their report. For discussion, first, opponent asks, what caused the magnetic damping? Reporter say that the rotation force is opposite to the magnetic force, then cause the damping. And we think that it is because the magnetic resistance force, which is opposite to the direction of rotation, since there are magnetic field in the experiment, so that when the magnetic field is bigger, the magnetic resistance force will also increase, then cause the damping more obvious. And opponent asks how the material affect the torsion constant. Reporter say it affects the torque of sphere oscillation, and we will agree with the reporter since the force of rotation become bigger and the magnetic resistance force still be the same, then this time the damping motion of the sphere will be decreased. And missing point for reporter lack of the accuracy of distance about testing magnetic field. And although the reporter calculate the torque, damping force should be considered since the damping motion is affected by the rotation force about the magnetic force. For the opponent, like to focus on the direction of the magnetic field, since the coupling force between the damping torque, rotation force, and the magnetic force could be the most important part in this experiment, and to focus on the formula that the reporter didn't done, since they can discuss more about the initial condition about release angles.
Okay.
Thank you.
So the reporter concludes remark.
I'm going to talk about the concluding remark. About theoretical, we could investigate the boundary condition of the magnetic field, and we should use the theoretical to principle more explain to our data, and we should consider more the damping in this theory. And about experimental, we could add more parameter like change the material of the wire and change the direction of our magnetic field and the distance between the coil and the sphere. And we could measure the torsion constant the wire we used and we could investigate the limitation of some parameter, such as the magnetic condition, the size of the ball. Yes, thank you.
So the question of Joe.
I have three questions to different presenters. So maybe firstly to the reviewer, you mentioned about the mass of the ball. So what do you think, how the mass can change the result? The mass of the ball. So probably during the time for the
Okay, so
opponent.
how does it-
I would like to ask a different question. Because you are talking about the vertical field.
Yeah.
Yeah, probably later on you can answer why. How do you think about the difference between horizontal and the vertical field?
So I think the main difference is that the magnetic force come from different like the different positions, right? So I think maybe this could affect the experiment that he done and the results that came out.
So we think if the density of it don't change, just change the size, the surface area will change. So that the area that causes the convection conversion and about the eddy current will be changed.
Thank you. So for the reporter, in your experiment you mentioned about the initial angle is critical to your effect, right? So how do you think, what's the mechanism? Because usually for simple harmonic motion, your initial angle or your amplitude will not change your period or your result. But in your experiment, you see a very clear effect of the initial condition.
The initial condition change the friction between the wire and the sphere.
The friction.
Different questions to different groups. To the reporters, just want to make sure I understand correctly. So I remember you say your tracker is limited up to 600 seconds, 10 minutes. Yes. But from this class, the data is limited to more than 1,000. What are the time?
We record the first 600 video, and when the rotation is longer than 600, and we could record another data.
So it means you have two different trackers or
We have two videos.
two videos from two different trackers.
Tracker is the software we use to analyze the motion.
You record the first part and the
Yes.
next part.
So you make sure the transition is smooth. Then you mentioned the magnetic field is uniform. So will you make sure that from the data?
We
You
use
have
the
data to make sure that the magnetic field is uniform?
pardon?
The magnetic field is uniform, is data, right?
Yes.
So do you have any data to confirm that the magnetic field is uniform on the surface of the ball?
Maybe we can do more data about we use the Gauss meter to measure our magnetic field.
So I just want to make sure you don't have that data in this report. So to the opponent, you keep mentioning the periodic motion.
Yeah.
What do you mean by that?
Because it is mentioned in the presentation that it is a torsion movement, right? So if it's a torsion movement, it would have a periodic motion that would affected by the
Periodic motion from what?
like
the swinging or the rotation?
the rotation.
So they do it.
Yeah.
So the reviewer, you said the torque damping. What do you mean by the torque damping?
I mean, maybe it's a kind of undertaking motion since like the temperature is decreased, and maybe we can maybe in their experiment they can test the underdamping oscillation when it's the formula is bigger than 0 when it may be
I have a short question. Do you think that in this question, the oscillation means swing or rotation. Yeah, for you swing rotation. But it, okay. So how about you? The oscillation here in this problem, it means swing or rotation.
Maybe swing and rotation.
Swing and rotation.
I think both should be considered.
Okay. So, but that it's scoring time. For the recorder. The recorder. Okay.
Wait.
7, 8, 6, 6, 8.
7, 8, 6, 6, 8.
And for opponent. Okay. 6, 6, 7, 6, 8.
6, 6, 7, 6,
8.
8. Okay.
And for a reviewer. Okay, 5, 8, 7, 7, 8.
5, 8, 7, 7, 8.
Okay, so let's take a break. 4, 15.
And we would like to join problem number 1, record figures.
Accept, be accepted.
Okay, so problem number 1. 来，你帮他比赛。
Honorable judges and fellow competitors, and the reporter from Team CYJ, and my name is Moy. And today I now report flexible finger. For statements, the effect of flexible finger to be observed the drop dead of an alcohol mixture is that positive onto relative hands. However, the dynamics of the fingers influenced by relativeness parameters. And here I'm going to express the geometry is about different threshold extents of different threshold fingers. That's the second dynamics, the growing speed, and then on the area of the fingers. And here's my observation. And first, there will be constant diffusing motion from the center. And next, well, is diffusing, the threshold starts to appear, and then both of them stop. And here's my observation. And for the process, first they would start the diffusing motion, and the second step they will go to the vertical motion, and finally both of them stop. And here's my observation of alcohol, and we use different proportion of alcohol and ink to define this motion. And here's the results. And here's my observation of stroke speed. And we use, here's the stroke speed means how fast I drop the speed, not the speed, how fast the speed drops. It means I drop, for example, I drop 1 gram drop dead per second or per 3 seconds. And if the dropping speed is faster, the fingers go faster. And here's the definition of the fractal finger. And a fractal finger is the geometric phrase. They have still similarity in different skills, like fractal fingers can be described as fractal finger, just like the graph. And for different phases of the fractal fingering, then we can observe this process, just like, and it's the first is the gravitational effect, and the next is the Montgomery curl, and next is the surface tension. And from the process fractal and before them stop, then when to get certain pairs stability to explain the phenomenon, and there is still perturbation, and viscosity. For diffusion, because of the different gravity effects, then the motion would, just like the graph shows. And for the effect, because of the different rates of the evaporation, then we will get different surface tension in different positions, and cause the motion of just like the graph. And for diffusion, just like I mentioned, both of them stop because of the same surface tension from this chart, which shows if the surface tension of the air and the mixture times cosine theta, because the tension in the acrylic and the mixture cosine, right? And this keeps diffusing, and from opposite side, and we will stop diffusing. And for comparison between the Hellas cell and the experiments, the definition of the Hellas cell means there are 2 layers and the liquids in the 2 layers. And in my experiments, I see the top layer is the air, but the downside layer is the oil also. And for comparisons, next, here's my experiments equipment and for initial velocity, and the head and shoulder, the initial velocity of the head and shoulder is injected by the syringe, and the experiment is dropping velocity from the pilots. And for couple nonlinear partial differential equation, we can get three equations to do our simulation later. And to supplement error and stability, and we can use these two Gauss's law to explain this phenomenon, just like this equation. And next, we can use it to find when the velocity difference and we close to the perturbation in different places, then we can observe the motion. And for this formula, and we can observe when the viscosity difference then relates to the different viscosity, then the difference, we can observe the different process of the motion. And this is the initial speed and the viscosity difference. And here's about the viscosity. And we use console to analyze the data, and use the three equation to do a simulation, just like I've mentioned. And for my experiment setup, I use this equipment to do the experiments. And for my experiment setups, I use two kind of colors and use the constant temperature bath to maintain the temperature of the environment. For my experiment one, and this is my first parameter, and this is the concentration of the pollutants. And for parameters, I use different concentration and to observe this motion. And this is my console simulation. To observe that when the differential is low, and the viscosity different viscosity 1 divided by viscosity 2. And from this chart, we observe that when R is larger, then the pattern will be more complicated. And for comparison between the experiment and model, we observe in different proportion, and will lead to the different growing rates of the motion. And for it to explain why the wide ring around the center link, and because of the self tension of the cohesion, and because of the tank is thin, then the thing will stick into the board. And consequently, that's two phase flow when the experiment is the three phase flow, just like the graph shows. Experiments results. And for my analysis, and we observe that the maximum length of the fingers, just like this equation, we can use it to describe the length of the fingers. And I use image to analyze the results. And for analysis, I can find that when that is much heavier, then the error bar will be larger because of the water density and length of the fingers depend on how much ink flow into the fingers, and to observe its results. And for my analysis of the growing speed, we can observe this. We use this formula to calculate the motion. And for the growing speed results, we can observe this graph, and we can use it to analyze how the motion, and use it as our experiment results. And for comparisons, we can use this formula and this chart to show how difference and the error bar is just like that. And for concentration of the in-air mixture, for these experiments, we use different concentration of the in-air mixture. And here's the geometry of the different circumstances, just like the graph. And if we compare the experiments and theory here, you can observe that you will skip the Macron flow and just to the frictional like motion. And for current speed of the droplets, we can use this formula to analyze the motion. And for current speed of the droplets, and since the Macron flow is caused by the difference overall speed of the ring and the center, when there is less alcohol, evaporation difference will be significant enough, just like the graph. And on the other side, we can use this graph to find that when the construction of the mixture can have fractal finger, the current speed will have the significant growth. And for the speed of the droplets, you can use the different speed of the dropping droplets to analyze the experiments. And we can use the formula to describe the motion. And here's my results and this graph that graph shows. And I also simulated it with console to analyze its motion and its phenomenon, just like the video. And for my conclusion, and for theory, and the diffusion stopped because of the Marconi effect, and because of the thin surface tension, just like the graph. And for fractal fingering parts, this is caused by the variation in viscosity and activation, just like the graph, just like the formula shows. For conclusion of the concentration of acrylic paints, and we can observe this graph. And for the conclusion of the construction of the mixture, and if the ratio between the alcohol and the paints and 5 and 1, and if it's the definition of the fractal here. For the conclusion of the dropping speed of the droplets, we can observe this trend of the change of the parameters. And thanks you for attention.
Okay, so for the next question.
And did you control the temperature in your system? Control temperature.
Of course, just like I mentioned, I use.
And have you controlled the humidity in your experiment? Humidity.
Okay. In my theory, humidity is not.
Oh, so you didn't control it, right?
Yes.
Oh, okay. And have you controlled the volume of every droplet? Every drop of droplet?
You mean the volume?
The initial volume, yes. Have you controlled it?
Of course, because I use the.
So you have control it?
Yes.
Okay, thank you. And do you think evaporate is important? Because you use alcohol and alcohol will evaporate. So do you think it is important? Important or not?
Oh yes, evaporation is very important here.
Important. And in which condition the self-maintained instability will occur? In which condition? Self-maintained instability occur.
You want to show me? I will just continue that.
Oh, okay. Maybe later. And how do you know evaporation exists? Have you do any experiment to prove that? You said evaporation is important. So how did you know that evaporation exists?
Because of the because of the surface tension change, and we can use evaporation to explain why the.
And have you measured the viscosity of alcohol mixture and ink mixture? Have you measured the viscosity?
Yes.
Okay. And will the thickness of a no? And do you think it is possible for magnetic force and viscous force to cancel each other out?
Okay, so opponent prepare. Take the floor.
Hello everyone, I'm Zheng from Team ECN 1917, and today I'm going to opposing problem number 1, fractal finger. And for the problem statement said that if we have to investigate the geometry and the dynamic of a finger influenced by a reference parameter. So we will mainly focus on the process of the process of droplet fractal and the evolution of the size of the fingers and the reason for expand and why it was fractal. And for overview report, and they have shown us observation for the diffusion motion, fractal motion, and different kinds of concentration you will have, and a different dropping speed. And the definition of fractal finger, they use different phrases for diffusion, fractal, and both it was stuck. And for diffusion, they talk about surface tension. For theory part, they talk about what causes fractal. It's depending on the segmental instability. And also they use Darcy's law to explain the data. And they compare between the whole shows and the experiment. It's initial velocity. And they also use Young's equation. Young's equation means the three surface tension acts in the same time. And for Marangoni effect, and for experiment, they change the concentration of diluted acrylic paint and the concentration of the alcohol mixture and the concentration and the dropping speed. And the conclusion, they say a segmental instability and Marangoni effect that will cause fractal of a liquid. And the Marangoni effect will cause diffusion. And droplet speeds increase, the growing speed will increase. And since the concentration of alcohol mixture become bigger, the diffusion phenomena will become more obvious. And some advantages and suggestions. Let's explain the theory in detail for fractal fingering, for segmental instability simulation, and also Darcy's law. And quantitatively analysis of data. They do the comparison between the theoretical and experiment, and they also use console to simulate it. For some suggestion, they didn't explain the phenomena in detail. Only mention what will affect the phenomena, but they didn't illuminate how they affect the phenomena and when their principles come together. And lack of the error explanation why the maxima of a lens finger, and they don't control the humidity in the experiment. And they have talked about that evaporation is very important, but they don't control the humidity. Means they will affect the evaporation rate. And they didn't find out what's the limitation of a concentration. And for some point to be discussed, and I will discuss about the segmental instability. Segmental instability occurs when the viscosity is different. And I also will discuss about Marangoni effect and the diffusion of acrylic paint and alcohol. And for the geometry, I think they didn't analysis for geometry very well, and also limitation. For experiment part, I will mainly focus on the 3 experiments that the reporter have done. And I think I can move to the discussion part. Thank you. And could you please turn to a page with Marangoni flow, page 11.
Here.
So, why it will evaporate slower and it will cause lower surface tension?
Okay, because of the volume, just like I've mentioned that because the segment here is the thicker, right?
Yes. So it's thicker, it will evaporate slower. So why it will cause surface? So why it will cause surface tension lower?
Because of the change of the volume.
No, I think maybe you can explain in detail. For example, for surface tension, which surface tension is bigger? For water and here is alcohol. So
It's a mixture of alcohol and water.
yes, so it is a mixture of alcohol and water. So maybe you can explain it for here. It has evaporate. So the evaporation rate, which one is bigger? Alcohol or
Let me
water?
show you more in detail. Because if the evaporation rate of the alcohol, and it will cause the different surface tension here.
Yes. So maybe you can see, you need to talk about it. In the center, the proportion of the water is bigger, so it will cause the surface tension to be bigger. And here, the proportion of the water is smaller, so surface tension will be higher. And you said that you have measured viscosity, right? So which one has bigger viscosity?
You mean which one means which the range?
Or for segmental instability? Okay, interface we have segmental instability. 13. So here, segmental instability it only occurs when two have different viscosity. So have you measured viscosity?
How should means no? I use expression to describe the situation that we the experiment. I mean, sorry, could you repeat your question?
Have you measured viscosity? And because you want to use maybe you can interpret with your segmental instability. Because segmental instability is
Okay. But I have mentioned that the reason of the segmentary instability is caused by the difference of the pressure.
different of the pressure.
Yeah.
But segmental instability is caused by the different viscosity. So maybe you can discuss about which liquid. Sorry. And for segmental instability, and here is the ink, and here is isopropyl alcohol. Here is the alcohol mixture. So which one have more viscosity? Yes, which one is bigger? You know that. Which one is bigger? So yes, it is bigger. So it only cause when the different viscosity. But the segmental instability, you have shown that it only occurs when it's between the two plates. So I think segmental, yes.
Hence here, this is no.
No, I think segmental instability, it only occurs when the two plates, it will squeeze the alcohol. So
segmentary instability is described because of the pressure difference that will use it to describe the motion of the liquid.
I think maybe we have different opinion about it. And maybe we discuss it or we discuss another thing. And have you have this is the original droplet, and after it dropped it is so because of the gravity and becomes thinner. So
Yes.
can you describe why it's energy transfer?
Okay. From the process, it just there's this potential energy will decrease by and with toucher, what you say is that the potential is the millimeter.
So yes, so potential energy will become smaller, and then what it will transfer into which energy? Yes, the potential energy becomes smaller.
And the energy, you mean the moment you touch the plant or the process is diffusion?
It is because of gravity, so it will become thinner. Right? It will become thinner and expand. So it will transfer into kinetic energy. And also surface. And have you think about the diffusion of the alcohol and the ink diffusion? Means
Yes.
they will mix together.
Okay.
I mean mix together.
Because of the rate of the evaporation of water is very slow, right? So only consider the evaporation rate of the alcohol.
Yes.
Because it will more main reason of the phenomenon.
So I mean mix together. Have you ever think about the ink and the alcohol, they will mix together? Because it is all hydrophilic.
Yes.
So maybe they will mix together and
yeah.
then yes. So when you talk about a speed, maybe you have already considered about the magnetic flow speed. And you also need to consider what is diffusion speed. Because they will mix together and then and how can you explain the geometry? Because the problem statement said
Okay. I just use geometry to describe it. For example, gravity is like that. It is the finger and the diffusion process. And which one would you want me to describe it?
and
To explain more in detail.
And I think for here is for geometry. So maybe you need to discuss what the dimension is. Okay, I think we can take into experiment part and experiment part. And could you explain what will for example which parameter will affect the speed? The speed of and you have you have for your experiment data you have your what will affect by the parameter?
You mean the parameter affects the speed?
For your experimental data. And what have you researched in? You have researched in, for example, the length of a finger.
You mean measure can refers to the growth of speed? This or the parameter cause the
What will cause which parameter will cause the length of the finger become different?
Okay,
Which parameter will affect the length of the finger? Yes.
I have to describe it more in detail.
Yes.
Here we furnish problem we define the stop will identify the motion of the diffusion the finger and stuff, right? But in fact, because of the extra motion is too small and we can observe in our naked eye. So exactly it won't stop in the actual circumstance.
It won't stop. You mean which one won't stop?
The finger,
Oh, you mean it will keep track of?
it will rectangle in very very
Oh,
micro.
you mean it will keep freckle, and then it will
Yeah, that's
very micro. Oh,
yeah, but we
so
can observe it.
okay.
Yeah.
And how do you know it?
Because of the force, we can analyze them. Because the change of the environment of the just like I mentioned, sorry, I mentioned actually. Because of the relation of the surface, so it causes the motion of the finger continue. Also, it will involve of the circular stop. It won't get stuck.
Oh, I agree. And can you explain why do you use Darcy's law? Darcy's law because you only can use it corrosive media flow. It means maybe Darcy's law means for example when you have many so for here Darcy's law maybe means for example in the soil and you have many fiber on it, so it will become vertical like this. But here, maybe the object pen, the ink is not the porous media flow. Yes.
In fact, the structure of the acrylic pen is just like that.
How did you know it's just like that?
Because from its density or structure, you can know that it will part of the first will go to like next, just like series and whole.
Okay, if it is like a situation,
Yeah,
say
yeah.
the fractal is like inside it is not in here. So like
No, I just think that it will change the volume of the pouch. Because here you describing could describe your model more clearly.
no, I said that maybe we can't use Darcy's law.
First, I use Darcy's law to describe the difference of the part of the motion. From this formula, you can observe here's my result to observe is because of the change of the viscosity.
You mean which one can be discussed?
Mu2. Mu2 is the in my experiments.
And okay, let me go to the other question. Have you find a limit? So in which concentration and it won't fractal?
Oh, okay. For my experiment for concentration, here. Sure.
Okay, so you have
So-
final fractal.
Yeah, limits of the proportion between the water and the just have to be a proper proportion to lead to this motion.
And you have said that evaporator exists, right? So I can suggest you to do an experiment about you put the humidity is very high and then you can test if it will evaporate. And it means that it won't evaporate.
Okay,
So
hands up.
okay, thanks. And for summary the report, we have discussed about American force, which will caused by a surface tension lower, and American force is caused by a surface tension gradient difference. And the result is at the center the proportion of the water will be smaller. So and at the edge the proportion of the water will be bigger. So it will produce the surface tension reduced because of American effect. And also we discussed about sedimentary instability. And the viscosity should be considered because it will cause the pressure difference. And for diffusion, and the oxygen and alcohol are both hydrophilic, so they will mix together and diffusion speed should be considered. And we also discussed about Darcy's law, but I think Darcy's law it can't use in this experiment because it is only for the porous media flow, but the oxygen it is not this one. Yes, thank you.
Okay, so it's Miguel's turn.
So here's some questions for the reporter. So you said that you use console to show the simulation. Yes. Can you compare the simulation and the reality condition and tell me what is the difference between them?
Okay. Console simulation use this the equation just like I mentioned to simulate the motion of the of it, right?
Yes. So what is the main difference?
Because we in console we haven't considered the perturbation here because the perturbation is a random factor to affect the real motion in actual situation, right?
So only this one. And so for the next one, do you think that the finger will keep growing?
Yes, just like what you mentioned, like
Keep growing smaller.
smaller from in the micro, it's very micro, and we could observe in our naked eye, but it will continue growing.
So what do you think?
And I also agree with the reporter's opinion.
Okay. So also she mentioned that when the ink go into into the they make the ink stink. So how can you observe it like the ink under the
Okay, from my observation, I observed that a segment of the blood go to the bottom of the plane because I put the
Like the side view camera, yeah? Or
after the result will observe this results. I mean, from my observation, I can observe that acrylic is like is there, right? Yes. There's a part of the blood goes to the bottom of it.
okay. Did you use a plate, just single like a board, or use a petri dish to do these experiments?
You mean the plate here?
Yeah, or it is a petri dish or just a plate?
I use just a glass.
Do you think that if you use this a petri dish, how would that affect the results?
I think it won't affect.
Okay. How do you think about this?
I bring to the opponents.
Okay, this would be the end of my questions.
OK。这样的也。别太紧张。
Honorable juries and fellow commanders, under reviewer Jason Lee from the Distinction High School, and I'm going to review problem number 1, Flight of Fingers. So here's the summary of the report. So first they describe the phenomena of the fractal extent, and they think that there is some critical parameters like the growth speed, the length, and the areas of the fingers. And also they observed that the whole motion is from the diffusing to the fingers and then finally stop. And for the theoretical analysis, they mentioned the effect of the gravity, the magnetic effect, and surface tension, and maybe some of the loss and the evaporation. And for the experimental confirmation, there are some parameters that they choose to investigate, like the diffusion coefficient, the ink alcohol rate, and the initial dropping height. And for when the water becomes more, it will become blurry, and in the investigation, the ink alcohol rate works best when it is at 1 to 5. And also, if the dropping height is bigger, they will grow faster. So here are some pros and cons for the reporter. Firstly, they've got a good phenomenal demonstration, like they use the Thomson simulation, and also they've got some pictures which clearly shows the phenomena. And also they control the environmental condition by using like a machine which controls the temperature, but they didn't control the humidity, which reviewers believe that bots maybe could do that. And also they wrong calculated the dropping speed because they use the dropping distance and the dropping time, but it is not a just there should be acceleration in the dropping motion. And for this opponent's performance, they have good fluency and great delivery, and they use good time control in the short questions. Also, they finding out some critical questions and they're good summarizing for the reporters. But also, they didn't focus on the data, and some of the error bars are just become bigger and smaller. And for the discussion part, for opponent first asked about the segmentary stability and what is this do with the viscosity, what is this law means in this phenomena. And reporter thinks that it is the factor of the difference of the pressure. And for the opponent say that it is because of the viscosity and it will lead to the pressure difference and will with the opponent. And for the opponent's next question, they asked about the energy transformation, and we think that it will be mainly kinetic energy and the fluid to flow. And we think that because there is viscosity difference between them, so there might be something similar to the friction. So it will be just used up. Like for the next one, they asked about the fractal and if there is a limitation. So the reporter said things that it will keep growing, and the limitation has something to do with the concentration. And we think that the reporter could use console to show the simulation about this phenomenon, like if it is really keep growing smaller fingers. And also the opponent asked about where did the ink goes, like it is going down or not. And the reporter think that it will go in the acrylic pen, but we think that we will think that it will be related to the characteristics of the pen, like the viscosity and the concentration. So, and this is the end of my presentation.
The reporter.
And the reporter and I for the remark. For concluding remark, and for the fixing parts, I think just like the opponent said, the suggestion, and I actually considered humanity when I was doing the experiment because I might affect the results. And for the discussion points, the first, I think this is the most important part, which is the motion of the finger stop. From my opinion, because of the perturbation of the environment, and so the motion will not stop exactly. And the second, who's asking, well, how about the evaporation rate effect because of the alcohol's evaporation rates, and it will cause the different surface tension and to lead to the different motion of the part of the segments. Okay, here's all my presentation. Thank you for attention.
So, question for Jules.
You have slides just a simulation comparison between your data and the simulation expectation. Well, there's a variable for R.
Do we compare
Your simulation and your data.
Oh, okay.
This is the definition something like law, the ratio between the two viscosity or something like that. Maybe you can check it with the okay. You want to check your slide?
You mean the part that shows the
And at the same time, the opponent and the reviewers, you keep asking the humidity, the effect of humidity, right? So how do you think that will affect the result?
I think the humidity will affect the evaporation rate. And the evaporation rate, it will cause a surface tension gradient difference.
I know that. So quantitatively, if you do that for example for different days, how big effect that would be? How big effect the humidity can cause?
And since the humidity becomes bigger and the evaporation of the alcohol will become smaller, and when it becomes smaller, and the surface tension will become smaller, so it will cause the surface tension gradient become smaller, and the manganese flow will become slow. So when it becomes slow, it will influence the speed.
So do you think if I do the experiment today and tomorrow, the effect will be so large?
For humidity, I means that if they use a container and then put it on the system and then put many alcohol in it, so it is.
How about the review? You also mentioned humidity, right?
Like for our rigorous view, if the humidity in the air only affects the evaporation rate for the water, so but the water evaporation also plays a role in this phenomenon. So, but it won't be huge than the evaporation rate for the alcohol.
In my opinion, I think the humidity
It's not the humidity is not a question to you. My question is the comparison between your data and the simulation. You did not show that, right?
comparison between the experience and simulation. Oh, okay. In my simulation, I haven't considered the perturbation in the actual circumstance.
Follow up the simulation. So can you shortly answer or tell me that the plastic pressures is included in your simulation and what parameters you need to input?
Oh, okay. For my simulation of tinsel, and I use 3 formula to calculate the motion.
Here.
Okay, here. There's 3 formula, and for inputs, we have to. You can enter, for example, the velocity of the segment difference, just like the mixture and the of water and the alcohol. Then you can get different results, or you can use the concentration as the coefficient here.
For the review and the question mentioned that how the geometry and dynamics change by the relevant parameters. So do you have any other suggestion for the parameter that could be changed in the experiment?
I think the thickness of the pen, the thickness of the ink pen should be considered, and maybe this one.
And the parameter you think it should be critical to this effect?
For the temperature, like they didn't change it on the control. And for like the humidity, like what I just mentioned, we need to figure out what it does to this phenomenon.
May I clarify my answer to this professor?
Okay.
And for the humidity, and because we do an experiment in today or tomorrow, because the humidity only have a little difference, so maybe it won't affect a lot. Thank you.
So, scoring time. So, for a reporter, is 7, 7, 7, 6, 7.
7, 7, 7, 6, 7.
And for the opponent, 7, 7, 8, 6, 8.
7, 7, 6, 8, 7, 7, 8, 6, 8. Okay.
And for our reviewer, 7, 6, 7, 6, 7.
7, 6, 7, 6, 7.
So we have a 10-minute break. Okay. Opponent challenge order.
We would like to challenge problem number 12, West Canada.
Wait a second.
Okay. Okay, reporter present.
Okay, hello everyone, my name is Zhang Yun from Team ECN 1917. The topic that I'm going to talk about is problem number 10, rice kettlebells. So here's our problem statement. So first, take a vessel and pour some granular material into it. For example, rice. If you dig a spoon into it, then at a certain depth of immersion, you can lift the vessel and contents by holding the spoon. Explain this phenomenon and explore the relevant parameters of the system. And we will mainly focus on to study the force analysis for different systems and explain how does the depth, static friction coefficient, and the radius of the stick affect maximum static friction force. So here's our experiment video. As you can see that the vessel is filled with the rice and have an insert stick. And we use the passcode to connect the stick and lift the stick up. And the whole vessel will rise with it. So here's our force analysis. And it has 3 parts. The first, for stick, the black line here is the force that we lift the stick. And the yellow line here is the weight of the stick. We call it mg. And here, when the stick wants to move, and it will have a friction that rice gives to stick. And here for rice, the yellow line here is the weight of it. And the blue line here is that when the stick wants to move, but the rice will stay at the same place. So it will have a friction that the stick gives to rice. And here, the normal force here is between the stick, rice, and vessel. And when the rice wants to move, and it will also have a friction that the vessel gives to rice. And here, for vessel, the yellow line here is the weight of the vessel. And this is the friction that the rice gives to the vessel. So, for the whole system, when we lift out the stick, and it will have the friction that between the rice and the stick, and it will be offset. So, when the rice also wants to move, and it will have a friction that between the rice and the vessel, and it will be offset too. And the normal force here, they are the same strength, but the different direction, and all of it will be offset. So according to these 3, then we can know that in this system, the resultant force will be offset, and the resultant force will be 0. So according to this, then we can get this formula that the force will equals to the weight of the stick, rice, and vessel. So here is the theory about the silo effect. So the thing here is that we insert the stick into the certain depth, and we take a flat line into and enlarge to this picture like this. And the height of it is the dz. And because when we add the rice into it, the pressure will be increased here. And it will also have a longitudinal pressure. And here is the friction force. And why the function here we use this, the maximum friction force, is that because the data in my report, we calculate it for the maximum friction force. So we use this formula. And here, when we suppose the friction force on site A reach maximum, then the sigma r will equals to the pressure multiplied by pressure steering constant, which is about 0.3. And these two formula is talk about the resultant force in this system will be 0. So we can get this formula, then we can calculate the pressure of Z. And here, so according to this formula, then when the e to the power of -3 is about 0.95, and which means that it is about the pressure, it is 95% of the maximum pressure. So when it is at this situation, the Z will equals to 3 lambda, like because of here. And so when the Z is very large, smaller than lambda, the pressure will similar to log Z, which is a quadratic function. And it means that when we when we add the rice into the vessel, the pressure of it will increase. And when the Z is bigger than 3 lambda here, and the pressure of it will be the log 3 lambda, and it is a straight line, which means that although we still add the rice into the vessel, but the pressure of it will not be increased. So it is about the normal force. Because a rise in this system is very small, so when we need to calculate the normal force, we need to use this formula. And here, let's notice here the 2 pi r. Why it is this? Because it is a content area at here, and we can get this formula. So according to this formula, then we can know when the z is much smaller than lambda, the normal force will proportional to the z squared, and which is a quadratic function. And here, when z is more bigger than 3 lambda, then here it will be a linear function, which is a straight line at here. So here's about our setup. Here's our force measurement. We call it Pascal, and here's the Pascal data collector, and the data will show on our phone. And here, as I just said, we calculate the maximum friction force, and it is the moment that the stick just moves. So this point, it just starts to move, and we will take this data to use that formula to calculate our data. So here is our first parameter. Then we change the depth of immersion. Here, as you can see that here's the depth, and here's the maximum static friction. So that's as you can see that when the depth increase, the maximum static friction will also increase. And according to the formula that I just said, when the depth increase, and this will be small, and because this is the negative, so the pressure of Z will be increased. And because the pressure of Z is increased, then we can know the maximum static friction will increase. So we can know that this data is correct because of this. And here, the lambda here, that we know it is 14. So the line, the depth here, it is not a quadratic function or other function. So we just fit it as a 1 times, 2 times, 3 times, 4 times function, and we found out that the 4 times function to fit it is the most accuracy. So we use 4 times function to fit it. And here, the y is changed to the normal force. So as you can see that here, when the depth increase, the maximum static friction will also increase. And according to this formula and this chart, then we can get the normal force will increase. And here we also use the 4 times function to calculate it. And here is our second parameter about that we change the static friction coefficient of the stick. That stick connect to the rise. Yes. So here is the static friction coefficient, and here's the maximum static friction. So as you can see that when the depth increase, then the static friction coefficient will also be increased, and it will cause the normal force increase. And according to this and this chart, then we can get the maximum static friction force will be increased like this. So here we discuss the depth and the static friction coefficient together. So here's the static friction coefficient, and here's the maximum static friction. And the different color here is the different depth of it. So let's look at this. When it is at the same coefficient, then when the depth increase, it's bigger than this. When the depth increase, then the maximum static friction will also be increased. Here, if it is when it is at the same depth here, then when the coefficient increase, then the maximum static friction will also be increased. So here's our third parameter of that we change the radius of the stick. Okay. So as you can see that here is the radius of the stick, and here's the maximum static friction. So when the radius of the stick increase, which means that the contact area between the rice and the stick will be increased. So the maximum static friction will also be increased like this. So here's our conclusion. The depth of immersion increase, then the maximum static friction will also increase. When the static friction coefficient of stick increase, then the maximum static friction will also be increased. When the radius of the stick increase, then the maximum static friction will also be increased. So thank you for your attention.
So, next question.
So here are some questions from your opponent. So first you use hand to pull the rod, right?
Can you louder?
Like you use your hand to pull the rod, right?
To pull
Like
the
meter?
stick.
Yes.
You mean with the
Like you use your hand to pull the stick. Yes.
Yes, but we use Pascal to connect
Okay.
it. So
So for the second one, could you turn to page? Could you turn to page 13? Right. You strongly trim that, and why did you choose the power before? Like the trend line. Why did you choose the power before?
I just say that because it is just a proof not belongs to any function. So we fit it. We tried many to fix it, and we found out that the fourth function is the most accurate.
Okay. And did you make sure your stick is vertical to ground? It's vertical?
Yes,
How did you do?
because when we
Like,
No.
you use a vertical meter?
maybe we can.
Meter?
Yes.
So for the next question, what can you explain what this equation means?
I mean this.
Yes.
Oh, okay. Let's turn to the theory.
So what does it prove? What does it prove in your experiment?
It just want to calculate the pressure of the stick.
Okay. So also, how did you calculate the static friction coefficient of your stick?
Static friction coefficient.
Yes. So time is up.
Oh wait. Okay.
The very useful of the opponent. Okay, and then take the floor.
So, honorable juries and fellow commenters, I'm the opponent Jason Lee from the physics team, Kingdom High School, and I'm going to oppose problem number 12, Marcella Wells. So here's the problem statement. The problem statement wants us to take a vessel and put some random material in it and investigate what at a certain depth of immersion you can leave the vessel and contents while pulling the spring. And he wanted us to explain this phenomenon and explore the relevant areas of the system. And in their presentation, they mainly focus on the force analysis, and they also investigate the parameters of the depth, the static friction, and the radius of the rod. So here's the proposed structure. They started with the observation video, which shows the phenomenon clearly, and also they use in their theoretical model, they use the force analysis and mainly the style effect for the whole phenomenon. And for the setup, they use Pascal to measure the force that it provides, and also they use tempo, which is maybe cause some mistakes we'll talk about later. We'll talk about it later. And for the experimentation, they investigate the parameters of the depth and the static friction and the radius of the rod. And for the conclusion, they think that bigger depth, the static friction and the radius of the rod will cause a bigger force. So here are some strong and weak points for the presenter. First, they got a clear delivery, and also they provide a complete force analysis model for the phenomenon. And also, they use hand pull, which may cause maybe some slightly side force or maybe other else uncertainties to the phenomenon. And also, they told us they use the power of the equation to draw the straight line, but in our opponent's view, we think that it is unclear and there's no obvious reason to use that. And also, there are lack of the investigation about the granular material, like the radius of length and the radius length and the friction force coefficient of them. So here are some points to be discussed, and presenter, please.
Okay. And then discuss.
So for the previous question for static friction coefficient,
Yes.
how do you measure it?
Okay, so we use, because we changed the coefficient and we use different sandpaper. So we post the sandpaper at here, and it is the container. So when and we have a glass that has the rise, and we put it on here. And when we change the angle of this, and at a certain angle, the rise of it will flow down.
So do you mean like this one is the stick or device for the spirit above it?
Here is the different sandpaper.
Sandpaper, but
Yeah, and here is the rocks.
But in your instrumentation, there's no sandpaper. And why did you use sandpaper too? And
Because the sandpaper is our different coefficient.
also, you mean like you use sandpaper to stick
change
on
the coefficient.
Okay. And for the hand pulling, which I some problems of it, and
Yes.
because hand pulling will not produce a stable force. So, in our opponent's view, it might provide unstable views, and it might let the meter produce random errors, maybe because of the unstable force.
Yes, it means
So how do you-
that's not accuracy.
Yes, because your hands might be a little bit shaky, but you cannot feel it. So the meter will feel it, but it might cause some inaccuracy.
Okay, I want to say that of this data, at one point that we do the experiment for 5 times. So every time we did it and we use it, we have calculated the times that we used to lift up. So I think it maybe cause the error, but because the times that we did it is very much, so I think the error will be very small.
Okay. But in our practice, you could still try to like minimize the errors, like from minimize the errors. Try how you hard to minimize the errors. Like using the motor, or maybe something to pull a string above it.
I think your question. Okay, you can say it again.
So the setup.
Set up.
Yeah, setup.
Okay.
Like because like for this picture,
Yes.
the meter is not like what is did you have a video of your measuring,
Measuring.
like the first
Okay.
of the video? It might cause then, as you can see, the vessel underneath it will cause some
Oh, wait,
slightly.
but
Yes.
that's not the way that we calculate our data.
Yeah,
We
how do you
use,
say that?
the setup is like this, but because we want to know the maximum friction force, right?
Yes.
So it is the moment that the stick start to move. So it's not like this. This is the static friction, not the maximum.
Okay, so if it is like this, when does the stick start to move?
Okay, so we will control it. It is at the vessel will be at the table, and we lift up the stick.
Yes.
And because at the setup that I just showed a chart like this, so we will control the time here.
Yes.
It is about the 5 seconds. So I think that every time that the force that we use will be just increase, and the stick start to move at the 5 seconds.
So do you like you fix your vessels on the table and pull it like gradually add your force?
Yes.
Gradually.
Yes.
So it might still cause some error because you might not really gradually add up your force.
Yeah, but I just say that we did it many times, and we have done it the average. The dot here is the average of it, and because it has very time, and as you can as you just say, it is because that we use hand to pull it, and maybe it is not every time it's 5.0 second. Maybe it is 4.5, so it will have an error here, but I think it is not a very big error.
That's fine. And also, if you use this way to measure, then how do you know if there is friction force between the rod and the rice, or the rice and the vessel?
And it is because that when we lift up the stick,
Yes.
and the stick will start to move, right?
But
But the rice will still in the vessel, right?
yes, but then just like what I mentioned, the rice won't just fly out, and because the friction between the rice and the vessel cannot afford the force you added, so it will cause it will make the rice like a fluid maybe, so it will not provide a solid structure to hold the stick. You know what I mean?
I think because in our observer that we just found out that when we lift up the stick, most of the rice won't move, but the surface of the rice, and I think it is because just like when you have a sand in your hand and you like this, and it will just like a rigid body, but when you hit it, just like the stick lift up, and it will just move back to the fluid, but it is just a surface of the rice.
Okay, and for the next question, the rice is not a perfect speed, yes?
Yes.
So why did you calculate your force analysis like this, like that? Because it won't be arranged like only this way.
Yes, but I just say that
Yes.
here.
Here.
Oh, no, I think it is here, right?
No, I mean what I mean is like the arrangement, the structure of the rice is not just like the picture of drawing. It won't be arranged only one way.
Yeah, I just draw a part of it, but and it is that we think of it, but most of it is at different directions, right?
Yes.
You mean that? But because we want to know is that when we sum it up, and it will cause the offset, and because of offset, so the resonant force will be 0, and because of 0, and when we lift up the stick, the whole container will rise with it.
Okay, but this is not a force. Actually, this is not a force that you add on the stick. The force you get a final force. The force is the friction force between the just like you mentioned this the friction force between the stick and the rise. But it is not the whole weight of the.
Okay, I think maybe you can draw a picture like a force analysis.
Like because the force here is the minimum force to let the whole system to move up. Like what? Chalk. Like if you want to let the whole system to move up, the minimum force is that. But if you add a fixed plane, it will cause so like the system won't move up, only the stick will move up. So the force you measure is only the friction between this one.
Not only friction,
Like
but also the
but you mentioned that you mentioned that your system is fixed on the table.
and this when we calculate the data. But I don't know. Now you say the situation is that when we calculate the data, or it is just for the problem statement.
Maybe restate it again. So in your rise, in your force analysis, the rise structure is like this, but in reality, it doesn't look like this. And you mentioned that the force there is you want to lift the whole system up. So the force will like this, but you forgot the force given by this maybe screw or maybe table. So what is this force given from the table? It is to that it will offset the other force and only let the rise and the stick friction.
Okay, but I think we need to research the force that between the stick and rise and the vessel, right? But here, no, I don't think you have the correct research of the.
What I mean is like you fix your vessel on a table. Yes.
Yes.
So the force here is not the force you've measured. Right?
Okay, but I think you have to know that here the data I want to collect is according to this.
Yes.
According to this formula, right?
Yes.
Yes, and it is just like so.
Okay, time's up. The opponent summarized the discussion.
So from the previous discussion, we talked about some problems with her experimental setup, and in our point of view, we think a setup should not be pulled by hand, or it should be pulled by a model or anything else. And also, in the theoretical model, we think that the rise arrangement is not correct for the real situation. So we think that it should be fixed and not, and this is not only the force from like this. And this is my summary. Thanks for listening.
Okay. So You understand?
Okay. So first, I wanted to ask the reporter about, do you think of changing the different material of granular material? Did you think of changing the granular material?
Yes, but if we change the material, then a lot of things will be changed in our real experiment.
Okay, so if we talk about just one parameter, what do you think if you change the volume of the granular material, it would affect? What do you think it would affect?
I think, but just like when we change the shape of
Yeah, but if you just only consider one,
consider what? But
just
I think
consider volume of the.
I think it can do it.
Oh no, just what would it change?
Or we change.
What would it change the result?
Consider one of the material.
Consider just one aspect of the parameter.
Okay.
We'll skip this question.
Okay.
Do you think there are boundary limits for the parameter you've done?
Have limits?
Yeah, boundary limits.
Yes.
Okay, so what does the opponent think that the boundary limits should be like?
Like what you mean by talking about
Okay.
boundary limits?
So the parameters, different parameters.
Yes. So within in our reference field,
So sorry. Call communication is not allowed. Please don't speak too well.
if force the maximum force we put we add on the stick, and what they measure is the boundary condition of that.
Okay, so like the different, like every parameter, like the height of the rise. So if you reach a specific height, would it like have the boundary?
Yes.
Okay, so we'll skip the question. No, let's skip it. Also, so you mentioned the force analysis, right?
Yes.
And the and do you think that polarizing the vessel can be used in the analysis? Can be analysis like that?
All arise. Oh, I think we just can take the average because it is. We can sum it, but we can take one of it because every time that we add the rise into it, the situation of it, the picking of it will be changed.
Yeah.
Will be different, right?
Okay, so yeah, so do you think that what do you think about for analysis or?
We just can see the whole of the system.
Okay, hands up. For repair is prepared. will take the floor.
Okay. Okay, so I'm the reviewer of Team CYJ. My name is Brian Ho, and today I'm gonna review problem number 12, rice kettlebell. So the problem statement are: take a vessel and pour some granular material into it. For example, rice. If you dip a spoon into it, then at a certain depth of immersion, you can lift the vessel and complete the test by holding the spoon. Explain the phenomenon and explore the relevant parameters of the system. So the main focuses are, there are two main focuses. Study the force analysis for a different system and explain how does the depth, static friction, and the radius of the stick affect the result. So now we talked about the summary and the comment of the reporter. So the theory they uses are force analysis, like normal force, friction, gravity, and second are the silo effect. And the experiment parameter includes the depth of immersion, static friction coefficient, and the radius of the stick. And the conclusion are the bigger depth, you can change the result. Okay, so the advantages for the reporter are a good time control, and they have enough amount of chart to help us understanding this experiment, and she can describe the theory like force analysis clearly. And the suggestion I want to give to the opponent is to answer opponent's question, and to the reporter is to answer opponent's question more accurately and on a clear trend line. And although in the graph you did not explain it, then lack of parameters. I think there should be more to be discussed, like the volume of the the granular materials should be considered. And then compare the experiment to the theory. And now it's a summary and comment of the opponent. The advantages are good time control, and he described the question clearly. But the suggestions I want to give to the opponents are he's too focused on the theory part. And now the summary and comment of the discussion. So the opponent asked, why did you use a stained paper to have the friction, like the friction coefficient? And the reporter said that they used it to change the friction coefficient. And the reviewer's opinion thinks that it's a proper method. And next, the opponent asked, have you controlled the force? And the reporter said, they select the average to solve it. And the reviewer thinks that the reporter could do some methods to check it in the experiment. And now let's talk about my question. So I asked about how was the boundary force, and the reporter said that they didn't conclude it in the presentation, and the opponent thinks that there should be the boundary forces, and the reviewer thinks that the reporter should consider it as a crucial part of a presentation. Next, I asked, do you think all rice can be analyzed like the model? Reporters said that they select the average, and in my opinion, they should consider all of the rice. And there are the missed points. So the discussion about granular material are missed, and the boundary limits, and the discussion about boundary limits are also not included in this discussion. So that's all. Thanks.
Okay, hands up. So the reporter conclude the remark.
Okay, I'm going to conclude my report. So, for the opponent, you said about the error, and we think that the error of data should not be the big factor of this topic, and although we use the hand to lift it up. And I just forgot to say that we precisely know how big the force is and revised with Pascal and Sprout view. And besides, according to the experiment data, we have done a lot of time and average of it. And here, as for the force diagram we just talked about, in our opinion, the normal force comes from the table. It's not the force which makes the vessel lifting up the rice, and instead, it should be the normal force and the static friction between the vessel and rice cause the phenomenon. And as for why the rice won't like the fluid slide down, we think that it is when putting rice into the container, the bottom pressure will be bigger and the situation will like the rigid body. So and the upper pressure is small, so which is close to the fluid. So only the surface of the rice is easy to be destroyed when lifting up the vessel. And here, when we lift the vessel with rice by the stick, and it will have the force. And from our analysis divide to 4 systems, we finally can know the pulling force is all of the weight. So for the silo effect, we know when the depth is over lambda, over 3 lambda, the pressure and the normal force and friction will not change more. So for the experiment, we change the depth of immersion and the static friction force and the radius of the stick. Then when the contents area between the stick and rice increase, the friction and normal force also increase.
Okay.
And thank you for your attention.
Okay. And then this question for
To the reporter, I have 2 questions. One side, you change the surface of your stick.
The surface
I don't understand very well. You change the surface by using different sandpaper. Is it?
Surface
Of the stick. Because you are talking about that you change the sticking the coefficient.
Yes.
So how do you change it? You change it by different sandpaper or?
No, we just use a stick and we post like a paper and different kinds of sandpaper on
Okay.
it.
Okay. And another question, then go to page 14. Now, how did you get the lambda of 14?
The lambda, okay.
You get it by fitting or by calculation?
Calculation. And here's the way that we calculate the lambda, like here.
Okay. Okay. So do you think it's comparable with your result in page 14? By calculation, you get lambda equals 14, around 14 centimeter.
Yes, I think it is correct in my experience.
Okay, thank you. And for the opponent, you mentioned about the arrangement of material. Do you think it's critical?
Yes, because the structure of the rice forms will definitely affect if it is the rigid body structure or it is the fluid structure.
Okay. For the reviewer, you mentioned about the boundary limit. I don't understand very well.
Okay, so so now we're talking about like the depth of the rice. So like I think there is like the one height of there should be the height of the mass that if they pull up, they cannot pull the vessel up. Like there should be the height that they can pull the vessel up, and there should be also the height that they can pull the vessel up. So I want to ask the reporter about what is the boundary limit from they can pull it up
So
and
the
they can
critical depths.
Yeah.
Okay, thank you.
Okay, so any other question? Okay, so it's drawing time.
Let's make sure this, in this plot, so the equation you show is the pressure, right? Yeah. The equation is about the pressure.
Yes, pressure of the sea.
And then, but when you do the data comparison, just do the kind of polynomial fitting.
Oh,
So it's not really the fitting to comparison to the theory equation. Am I understand correctly?
yes, and maybe we can do it in a because here it is the depth of it, and it can cause the pressure of it increase, and because the pressure is equals to the force and
Okay, I got it, but is there any relation between this polynomial? Can you take the polynomial to the correlation to this exponential function. Can you do that?
Or you mean that to have this, to fit
Well,
this chart?
Yeah, even you use a polynomial, but they must have some correlation between these two, right? Can you do this?
I think.
How to do?
I think we can use the GeoGebra to have this line and to fit these two.
And another question is about the kappa. 0.3, roughly 0.3. Somebody else knows? You have a parameter for kappa, right? Or k, I don't know. And it's about 0.3.
You mean salary, right?
Yeah. Right. So how do you get this number? Yeah.
Here
Yeah.
and which?
The k.
Oh, k. Because k is a constant.
How do you get it?
Because
Measure it or you take it from the literature.
yes, it's just from the
Literature?
Okay. Scoring time. First order reporter is A7A. Six, seven.
8, 7, 8, 6, 7.
The order corner. 6, 7, 7, 7, 6.
6, 7, 7, 7, 6.
For the reviewer, it's 6, 6, 7, 7, 6.
6, 6, 7, 7, 6.
Okay, so it's over.